Welcome, curious minds, to the deep dive. Today, we're embarking on an incredible journey right into the heart of chemistry. We're talking about building things, but not with bricks and mortar. No, this is building with atoms and molecules.
Yeah, it's pretty mind-blowing stuff.
Imagine, if you will, trying to build this incredibly intricate mansion, multiple rooms, complex structure. But here's the catch. Every tiny piece, every atom needs to be perfectly placed. You can't knock anything over you've already built.
And sometimes you even need to temporarily cover a window, maybe, while you paint a wall,
Right.
and then uncover it later perfectly. That's really what multi-step organic synthesis is like. It's this complex, sometimes just breathtaking world.
It really sounds like it pushes the limits, Demands science, demands creativity.
Absolutely.
Yeah.
And in this deep dive, our mission really is to give you a shortcut, way to get well informed on the brilliant strategies chemists use to create these new complex molecules.
That's right. Our source for this is a foundational chapter from Advanced Organic Chemistry, Part B, Reactions and Synthesis, the 5th edition. We're going to unpack the core concepts, these ingenious tactical tools.
And we'll even walk through some real-world examples, some masterpiece syntheses of natural products.
Yeah, you'll get to see how chemists tackle these huge challenges, not just the what, but really the why, how these molecular marvels are actually built. So let's dive in, shall we?
Let's do it. So maybe we should start with the basics. Why are multi-step syntheses even necessary? Why not just do one reaction?
Right, because in a basic chem lab, you learn reaction A goes to B, C goes to D, simple steps.
Exactly. And those reactions often work beautifully in isolation, under very specific controlled conditions.
Like learning to hammer a nail or maybe paint one wall. But if you want to build a whole house, well, suddenly those simple tasks are part of a much bigger, much more complicated plan. Everything has to fit.
That's the perfect analogy. Building a new complex molecule, especially something from nature, maybe something with medicinal potential, it requires a strategy, a grand strategy. And the crucial challenge, the thing you always have to worry about, is that the reactions in your sequence must be mutually compatible.
Meaning
you can't have one part of your molecule that you just carefully put together suddenly reacting with something else you're adding in the next step.
Yeah.
It's like a delicate dance.
Yes.
Every functional group, every reactive part of the molecule has its own personality, its own reactivity. And you need to anticipate and avoid any unwanted side reactions as you go through maybe dozens of steps.
Okay, so it's molecular choreography. How do chemists actually manage that? The source mentions these technical tools, 2 foundational ones.
Yeah, 2 really key tools. The first one is protective groups.
Okay.
These are basically temporary chemical modifications. You take a functional group, say an alcohol or an amine, something reactive, and you temporarily change it, mask it, so it won't react during a specific step.
Like putting a cap on it?
Exactly like putting a cap on it. Then, once you've done the reaction you needed to do elsewhere on the molecule, you remove the protective group, and voila, your original functional group is back, unharmed.
I see. So you protect the windows while you paint the walls, then take the protection off. That makes sense?
Precisely. The second tool is synthetic equivalent groups.
The stand-in actor idea.
Yeah, kind of. Sometimes the functional group you want doesn't have the right reactivity for the job you need it to do right then. Maybe you need something that's normally electron poor, an electrophile, to act like it's electron rich, a nucleophile, like wanting an acyl group to behave like an anion.
Which it normally wouldn't do.
Right. So a synthetic equivalent group lets you introduce that functionality using an alternative structure, one that can react the way you need it to. Then later on, you convert that structure into the actual functional group you wanted all along. It's like the stand-in performs a tricky stunt, and then the main actor steps back in.
Okay. Clever tools for specific problems. But how do you even start planning something this intricate? You don't just mix stuff together and hope, right?
Oh, definitely not. Hope is not a strategy here.
Yeah.
This brings us to the grand strategy, retrosynthetic analysis. This is absolutely fundamental. It's the main way chemists plan complex syntheses.
And it works backwards.
Exactly. Instead of starting with simple chemicals and building forward, you start with your final target molecule, the mansion, and you work backwards on paper. You dissect it, step by step, breaking key bonds.
Like saying, okay, to build this part, what must have come right before it, deconstructing it mentally.
Precisely. You break it down along reasonable chemical pathways into successively simpler compounds. You keep going until you reach things that are either commercially available or really easy to make.
And there's a special symbol for this backward step.
Yes, to show that these are disconnections that correspond to real, feasible synthetic reactions in the forward direction, chemists use an antisynthetic transform. It's shown as an open arrow, like LiAlH₄. It emphasizes you're thinking in reverse, but each reverse step has to map onto a plausible forward reaction.
Got it. It's not just drawing lines, it's thinking about actual chemistry in reverse. And what about these synthons?
Right, synthons. These are the sort of idealized building blocks that your retrosynthetic analysis suggests. They're the fragments you imagine coming together. But a synthon isn't just a piece of the structure. It also has to imply the correct reactivity for the bond formation when you run the reaction forward.
So if you're planning, say, an aldol reaction.
Exactly. If you disconnect to reveal fragments for an aldol reaction, one synthon needs to represent the nucleophilic part, the electron donor, and the other needs to represent the electrophilic part, the electron acceptor. They have to have complementary reactivity.
This sounds like a really creative puzzle. Is there just one right answer, one perfect synthesis?
And this is one of the most fascinating aspects. There is absolutely no single correct solution. Synthesis is a massive intellectual challenge. It really puts a premium on creativity, on ingenuity. Different chemists can, and often do, come up with totally different routes to the same molecule. Each one might be elegant, valid, but have different pros and cons.
Wow, that really highlights the art within the science. So given there's no single right way, what guides chemists? What factors do they weigh when designing these complex routes?
Several critical things. First, just the sheer complexity of the target molecule itself. How big is it? How many functional groups does it have? And crucially, how many stereogenic centers?
Those are the 3D arrangement points, right? Like left and right hand.
Exactly. Atoms, usually carbon, where switching two groups gives you a different non-superimposable mirror image molecule, and an enantiomer. But if a molecule has many of these centers, controlling that precise 3D arrangement at the stereochemistry becomes a massive challenge, especially if you need an enantiomerically pure product, just the left hand, not a mix. You need absolute control.
So 3D structure is paramount. What else?
Then you have the practical constraints. What do the starting materials cost? Is the route economically feasible if you wanted to make kilograms of this stuff for, say, a drug? Are the byproducts acceptable? Can you dispose of them safely? And of course, safety throughout the process is absolutely critical. A brilliant synthesis on paper is useless if it's too expensive or too dangerous to run practically.
Right, that blend of intellectual puzzle solving and real-world practicality. Now, speaking of practicality, you mentioned convergent synthesis earlier. How does that fit into the strategy and maybe help with efficiency?
Convergence. This is really, really important, especially for big, complex molecules. So a convergent synthesis is different from a linear one.
Linear being just step after step after step in one long line.
Right, starting with one thing and just adding pieces sequentially. In a conversion approach, you build several large fragments like branches of a tree independently, often in parallel, and then you bring these big pieces together near the end of the synthesis.
Okay, why is that better? Does it just save time because you're doing things in parallel?
It's much more than just saving time, although that can be a benefit. The real power comes from how overall yield works in synthesis. The total yield of a multi-step sequence is the product of the yields of each individual step. You multiply them together.
So if you have lots of steps.
Even if each step is pretty good, say 90% yield, in a long linear synthesis, the overall yield drops off dramatically. The losses compound with each step.
Can you give us an example? Because 90% sounds pretty good for one step.
Okay, let's take a simple linear 6-step synthesis. Each step is a solid 90% yield. Great, right. But multiply 0.9 by itself 6 times. 0.9 to the power of 6. And your overall yield is only about 53%.
Wow, you lose almost half your material even with good steps.
Exactly. Now imagine you can make that same molecule convergently. Maybe you build 2 fragments, each taking 3 steps, longest linear sequence is 3, and then combine them. Still 90% yield per step. Now the yield for the longest sequence, 0.9 cubed, is 72.9%. If the final coupling is also 90%, the overall yield jumps significantly. The source example shows the overall yield jumping to 73% by reducing the longest linear sequence from 6 to 3. That's a massive improvement in efficiency.
That's a huge difference, getting almost half as much product again from the same starting material.
And it gets even more dramatic with more complex molecules. Consider a 15-step linear synthesis. At 90% per step, the overall yield is a pitiful 8%. Just think, 92% of your starting material is gone. But if you can break that down convergently, say, into 3 branches of 4 steps each, then combine them, the source calculates the yield can jump to 48%. It underscores how critical strategic planning, like using convergence, is for making synthesis practical and efficient.
So it's a fundamental strategy for maximizing your output and minimizing waste, especially for things like drug manufacturing, where yield really matters.
Absolutely. Now let's circle back to those tactical tools. We mentioned synthetic equivalent groups for masking or changing reactivity.
Yeah, the stand-in actor thing. How does that actually work in practice? Let's get into the specifics.
Okay, this brings us to that fascinating concept of Umpoling. It's a German word, literally means polarity reversal.
Reversing the polarity.
Yeah, flipping the normal electronic character of a functional group. Think about an acyl group, like in an aldehyde or ketone. That carbonyl carbon is usually electrophilic, electron poor, it wants electrons. But sometimes your synthesis demands that carbon act as a nucleophile, an electron donor, like an acyl anion. That's Umpoling, making it do the opposite of its usual job.
Okay, how on earth do chemists achieve that flip?
There are some really clever tricks. One common way is using O-protected cyanohydrins. You start with an aldehyde, you react it to form a cyanohydrin, and then you protect the oxygen atom. Now, the carbon that used to be the carbonyl carbon, the one attached to the cyano group in the protected oxygen, can be deprotonated with a strong base.
Making it negatively charged, a carbanion.
Exactly. You get a nucleophilic carbanion, which the source labels A. This carbanion can now attack things, form carbon-carbon bonds in ways the original aldehyde never could. After it does its job, you just hydrolyze the protected cyanohydrin, and you get your carbonyl group back.
Wow. So you mask it, change its nature, let it react, then unmask it. That's thinking way ahead.
It really is. The source shows a nice example using this to put an acetyl group onto cyclohexanone. There are other ways too, like using lithium-vinyl ethers or certain organocuprates. These also act as masked acetylene equivalents that can be revealed later.
And you mentioned 1-glass-3,3 dithions are really versatile for this.
Oh yeah, dithions are classic Umpoling reagents. You form a cyclic thioacetal, usually from an aldehyde and 1,4-diotropanadithiol. Then you treat it with a strong base, like N-butyllithium. The hydrogens on the carbon between the 2 sulfur atoms are surprisingly acidic because the resulting carbanion is well stabilized by the sulfur atoms.
So the sulfurs make it easy to pull off a proton and create that negative charge.
Exactly. This lithiated dithion is a fantastic nucleophilic acyl equivalent. It reacts readily with things like alkyl halides or epoxides or even carbonyl compounds. Then later, you hydrolyze the dithion moiety, often using mercury salts or other methods, to reveal the carbonyl group. They're incredibly useful and pop up in many complex syntheses.
So this Umpoling idea isn't just for simple carbonyls. It can get more complex.
Oh yes, it extends to more complex species, sometimes called dipolar synthones or reagents with latent multiple functionalities. The source mentions cyclopropyl phosphonium ions, like structures 1 and 2. Yeah. These are fascinating because the strained cyclopropane ring itself holds both electrophilic and nucleophilic character, just waiting to be released.
How does that work? Both electron-loving and electron-giving in one?
Sort of, yeah. The ring strain makes the carbon susceptible to nucleophilic attack, acting electrophilic, but the ring opening can generate intermediates that are nucleophilic. This makes them great for complex ring-forming reactions, like cycloadditions.
Can you walk us through an example? That sounds pretty advanced.
Sure. Take that phosphonium salt 1 reacting with a Guidos ester. It forms cyclopentene derivatives in really good yield. It's a neat cascade. First, the enolate of the Guidos ester, that's the nucleophilic part, attacks the cyclopropane ring, opening it up. Here, the cyclopropyl carbons act as the electrophile. This generates a stabilized Wittig slide.
Okay, a Wittig slide. That's a species with adjacent positive and negative charges, often used to make alkenes.
Right. But here, this enolide intermediate then reacts internally with a ketone carbonyl group that was part of the original Beatty's Pfister. This intramolecular Wittig reaction closes the 5-membered ring. It's a really elegant way to build that cyclopentene structure.
So synthetic equivalents and Umpoling are powerful tools for accessing reactivity that isn't normally there, enabling really creative bond constructions.
Precisely. And this need for precise control leads directly into our next big strategic consideration, controlling stereochemistry.
Ah, yes, the 3D arrangement. Why is this so critical? A molecule's a molecule, right? Does the 3D shape really matter that much?
It matters enormously. Remember, for a molecule with unstereogenic centers, there are potentially 2n possible stereoisomers. Just 3 centers mean 8 possible isomers. 5 centers mean 32. If your synthesis doesn't control this, you get a mixture.
And mixtures are bad because...
Reduced yield of the one isomer you actually want, for starters. And often, these stereoisomers are incredibly difficult or even impossible to separate efficiently. For drugs, it's even more critical. Often, only one specific enantiomer, one mirror image, is biologically active. The other might be inactive, or worse, it could have harmful side effects.
The thalidomide example comes to mind. One version therapeutic, the other devastating. So getting an enantiomerically pure material is often the goal. How do chemists achieve that? What are the main strategies?
There are several main approaches. The first is resolution.
Okay, resolution.
Yep.
Like separating things out.
Exactly. You start with a racemic mixture, that 50.50 pix mix of enantiomers, or maybe even an acyl starting material that generates a racemic intermediate. Then, at some point, you separate the enantiomers. Often this involves temporarily converting them into diastereomers by reacting them with a pure chiral compound. Diastereomers are stereoisomers that are not mirror images, and they have different physical properties like solubility, so they can be separated by crystallization or chromatography. Then you convert them back.
But the downside is you're throwing half away, essentially.
Pretty much. The maximum yield of your desired enantiomer is only 50% from the racemic mixture. So it's inherently inefficient in terms of material, though sometimes it's the only practical way.
Okay, what's next?
Using an enantiomerically pure starting material, this is often called the chiral pool approach. You start your synthesis with a molecule that is already chiral and enantiomerically pure, often something readily available from nature like an amino acid, a sugar, or a terpene.
So you build the chirality in from the very beginning.
Right. You leverage the existing stereocenters. This can be very efficient, but you're limited to the chiral building blocks that are readily available and affordable, and the chirality is consumed in the process.
Makes sense. Strategy 3.
Using chiral reagents. These are reagents that are themselves enantiomerically pure and transfer their chirality during the reaction. You typically need a stoichiometric amount, meaning one molecule of reagent for each molecule of your substrate. Think of chiral reducing agents or hydroborating agents derived from chiral terpenes like pine. They get used up in the reaction, though sometimes the chiral part can be recovered.
Okay, stoichiometric. That can get expensive if the reagent is complex. What about chiral auxiliaries?
Auxiliaries are clever. A chiral auxiliary is an enantiomerically pure molecule that you temporarily attach to your substrate. Its job is to direct the stereochemical outcome of one or more reactions by using its own defined 3D shape to influence how reagents approach. It acts like a chiral steering group.
So it controls the reaction's direction.
Exactly. Then, once it's done its job and the desired stereochemistry is set in your molecule, you cleave the auxiliary off. And here's a key advantage. Often, you can recover the auxiliary and reuse it, which makes the whole process more economical and sustainable than using a stoichiometric chiral reagent that gets consumed.
That sounds very efficient. And the last one, the holy grail.
Chiral catalysts. This is really the ultimate goal in asymmetric synthesis. Here, you use only a small catalytic amount, maybe just 1 mol% or even less, of an enantiomerically pure substance. This catalyst directs the reaction to produce predominantly one enantiomer of the product.
So a tiny amount of the chiral catalyst can produce huge amounts of the chiral product.
In principle, yes. A single catalyst molecule can turn over many, many times, generating potentially vast quantities of enantiomerically pure product. This is by far the most efficient method in terms of atom economy and minimizing chiral waste. Think of enzymatic reactions or transition metal complexes with chiral ligands. It's where a lot of modern research is focused.
Okay, so those are the strategies. How does the control actually happen at the molecular level during a reaction?
Several ways. Existing functional groups in the molecule can play a role. They can exert steric control, meaning their physical bulk blocks approach from one side, or stereoelectronic control, where orbital interactions favor one pathway over another. For example, a hydroxyl group might coordinate to a metal catalyst, directing the reaction to occur on the same face of the molecule.
And existing chiral centers.
Existing chiral centers are huge influencers. They can lock the molecule into a preferred conformation, a specific 3D shape, which then dictates how the next reagent approaches. This is often seen in 1,3 or 1,4,3 asymmetric induction, where a stereocenter influences the formation of a new one nearby. Generally, the closer the new stereocenter is to the existing one, the stronger the influence. Chemists use models like the Falcon model or chelation control models to predict and explain these outcomes.
So it's clear that planning for stereochemistry isn't optional. It has to be baked into the synthetic plan from the very start, or you risk ending up with a mess that's hard to separate and gives poor yields.
Absolutely. It's a central part of the design process. And now that we've laid out these fundamental principles, retrosynthesis, tactical tools like protecting groups, and Pauling, convergence, stereo control strategies. Let's see them in action. We can dive into some specific examples, some real masterpieces of synthesis from the source.
Great. Let's kick off with Juvabione. You said this one's interesting because it shows lots of different approaches over time.
Exactly. Juvabione is a terpene, and its synthesis has been a playground for chemists to test different strategies. The early syntheses, shown in schemes 13.4 and 13.5, were racemic. They didn't control the enantiomeric outcome.
How do they approach it?
They often started from simple aromatic compounds, like derivatives of methoxybenzene. The key was using the Birch reduction to convert the aromatic ring into a cyclohexyidine or a cyclohexanone structure, setting up the six-membered ring. The methoxy group helps direct this reduction.
And then building the rest of the molecule.
Key bond formations involve reactions like the Reformasky reaction to build part of the side chain, C4C7 bond, and Grignard reactions for adding other carbon pieces. But a common problem in these early routes was that hydrogenation steps, used to reduce double bonds, weren't very stereoselective. They often got mixtures of diastereomers. Scheme 13.5 did try a more convergent approach, using a mixed aldol condensation to bring in a larger chunk of the side chain, which, as we discussed, helps with overall yield.
But still racemic. Did they try starting with something chiral from nature, the chiral pool idea?
Yes, that was the next logical step. Schemes 13.7 to 13.9 show syntheses, starting from terpene-derived materials like limone or perolaldehyde, which are naturally occurring and enantiomerically pure. The hope was to transfer that existing chirality into the Juvabione structure.
Did it work well?
Scheme 13.7 used hydroboration to try and set the stereochemistry at C4 relative to C7, but it only achieved modest stereoselectivity, a 3.2 mixture of diastereomers that still needed to be separated. So even starting chiral doesn't guarantee perfect control down the line.
Still tricky. What about syntheses that really focused on getting the relative stereochemistry right, distereoselective ones?
Right, those are shown in schemes 13.1 on and 13.1, often starting from cyclohexanone. Scheme 13.1 is pretty cool. It used a cycloaddition between an electron-rich aminamine and an anone, forming a four-membered ring intermediate, which then opened up. The key stereo control came from preferentially protonating an enamine intermediate from the less sterically hindered side. A subtle steric effect dictated the outcome.
And scheme 13.1 none, how did that achieve selectivity?
That one relied on the preferred conformation of the transition state for an oxycope rearrangement. This is a type of sigmatropic rearrangement. Even though the intermediate was a mix, both isomers funneled towards the desired product because the molecule preferred to adopt a specific chair-like shape during the reaction, minimizing steric strain. It's a beautiful example of conformational control.
Like the molecule itself finds the easiest 3D path. Very elegant. Okay, now for the ultimate goal. Enantiospecific syntheses getting just one mirror image.
Yes, aiming for a single enantiomer. Scheme 13.16 used a chiral sulfoxide as an auxiliary. It directed a stereoselective addition to cyclohexanone, likely through a chelated transition state where the metal coordinates to both the sulfoxide and the incoming reagent, forcing a specific approach. The sulfoxide did its job, helped introduce another piece, and was then removed.
A classic chiral auxiliary strategy. What about using biology?
Scheme 13.17 is a great example of biocatalysis. They use Baker's yeast for an enantioselective reduction of a symmetric bicyclic dione. This is a desymmetrization taking a symmetric molecule and making it chiral using a biological catalyst. Yeast enzymes can be remarkably selective. This route also featured an anionic 2-col-3 sigmatropic rearrangement.
Enzymes are powerful tools. Any other notable enantiospecific strategies?
Scheme 13.18 used kinetic resolution with lipase PS, another enzyme, separating enantiomers by reacting one faster than the other. It also had some clever ring expansion chemistry. Scheme 13.19 used a chromium tricarbonyl complex attached to the aromatic ring to achieve amazing regio and stereo control in an addition reaction, avoiding unfavorable steric interactions in the transition state. Scheme 13.20 tried a tandem Diels-Alder-Ireland Claisen rearrangement. Very efficient for building the skeleton, but unfortunately not very stereoselective, giving a mix. It's a reminder that sometimes there are trade-offs. And Scheme 13.21 started from an enantiopure lactone and used the shape of the existing ring system and a stereospecific palladium reaction to control subsequent steps.
So Juvabione really illustrates the whole toolbox, racemic, chiral pool, distereoselective, and enantiospecific methods using auxiliaries, catalysts, enzymes, rearrangements. A real case study in synthetic evolution.
Definitely. Now let's look at longifilene. This one looks significantly more complex structurally. Bridged rings. That looks tough.
Yeah, that intricate tricyclic structure is the main challenge. Corey's 1964 synthesis, schemes 13.23 and 13.24, was the first success, a real landmark. How did he tackle it?
His retrosynthetic analysis simplified the tricyclic structure back to a bicyclic one, envisioning an intramolecular Michael addition for the final ring closure. A really key step in the forward direction was a pinochle rearrangement, a carbocation rearrangement that allowed for ring expansion and migration of groups to build the core skeleton.
And he started from a known compound.
Yes, he started from the Wilkinson ketone, a very common and useful bicyclic starting material for terpenes and steroids. Its availability and known chemistry made it a strategic starting point. The final Michael addition required pretty harsh high-temperature conditions, but it worked.
A classic building block plus clever rearrangement. What about other routes to longafulline?
McMurray's synthesis, scheme 13.25, also started from the Wilkinson ketone, but used a different key step, an enolate opening an epoxide ring. This required careful setup of the relative stereochemistry earlier, specifically establishing a cis-ring fusion via hydrogenation. And then there's Johnson's synthesis, scheme 13.28. This one is described as striking and remarkably simple in its key step.
Simple for longafulline. That sounds amazing. What did he do?
He designed a precursor that underwent a cationic cyclization cascade. A single reaction step, triggered by acid, formed the entire tricyclic skeleton from a monocyclic starting material. What was brilliant was the symmetry of the intermediation. As the source says, no issues of stereochemistry arise until the carbon skeleton is formed, at which point all of the stereocenters are in the proper relative relationship. It completely sidestepped the tricky stereocontrol issues until the very end. Just incredibly elegant.
Wow, one-shot construction. That's strategic genius.
Any other interesting approaches? Schultz and Puig, scheme 13.30, used a Birch reduction and an intramolecular cycloaddition of a diazolalkane, followed by thermal decomposition of the resulting adduct to form the skeleton via a diradical intermediate. What's neat here is they showed this route could potentially be made enantiospecific by starting with a chiral precursor derived from L-proline, though it gave the unnatural enantiomer. And LiAlH₄, scheme 13.32, used an intramolecular Diels-Alder reaction as their key ring-forming step, another powerful strategy for building complex polycycles.
Okay, let's shift gears to the pre-log lactone. Smaller molecule, but looks packed with stereocenters. What's the challenge here?
Precisely that. Controlling all those adjacent stereocenters, C2, C3, C4, C5, C6, in the lactone ring and side chain. Grieco's synthesis, scheme 13.34, started with an enantiopure bicyclic material. The existing ring structure provided facial selectivity, guiding reactions to one side. Key steps included an exoselective alkylation and a Baeyer-Villiger oxidation coupled with an allylic rearrangement.
And this molecule seems like a prime target for that desymmetrization strategy we talked about earlier, starting with something symmetric.
Absolutely. Schemes 13.36 to 13.41 all start with derivatives of meso-2-I-dimethylglutaric acid, which has that internal plane of symmetry. The challenge is to perform a reaction that selectively modifies one half, breaking the symmetry and setting the stereocenters enantioselectively.
How did they achieve that?
Different ways. Hoffman, scheme 13.37, used chiral boron reagents for stereocontrol. Opolzer, scheme 13.39, had a very short route, using a boron-inosyltum chiral auxiliary to direct an aldol reaction with excellent anti-Felkin stereoselectivity. Yamaguchi, scheme 13.41, used enzymatic desymmetrization with a lipase. It shows the variety of tools available for this elegant strategy.
And chiral auxiliaries seem popular here too.
Very much so. The Evans oxalidinones, for example, feature prominently. Evans and Bartroli, scheme 13.45, and Martin and Gwynn, scheme 13.46, both leveraged oxalidinone chiral auxiliaries to direct stereoselective alkylations and aldol additions. The bulky auxiliary effectively blocks one face of the enolate, ensuring the reaction occurs from the other side with high fidelity.
Any other notable strategies for controlling the stereochemistry in this lactone?
Sy and Midland, scheme 13.51, based their control on a stereoselective 2.3 sigmatropic rearrangement, getting high selectivity for one isomer. And Campaign, scheme 13.51, used a modern enantioselective catalytic conjugate addition with a chiral copper binap catalyst, showcasing cutting-edge catalytic methods.
Okay, moving up in complexity again. Back in the third, the core of Taxol. That looks like a beast. What are the big hurdles?
Oh, it's incredibly complex. A dense polycyclic structure, that unique bridge taxane skeleton, and just loaded with oxygen functional groups and stereocenters. Managing all that reactivity and stereochemistry simultaneously is a monumental task.
So protecting groups must be essential here.
Absolutely essential. Holden's synthesis scheme 13.53, one of the first successful taxol syntheses, which goes through back in the third, made extensive use of protecting groups like TES and bomb ethers right from the start to mask all those reactive hydroxyl groups. You just have to shield them while you build the core.
Protecting everything that could react accidentally.
Pretty much. Key steps in Holden's route included an aldol addition to form the C ring and a really clever cyclic carbonate rearrangement to form a lactone. And the final step to install the C2-benzoate group is fascinating. Adding phenyllithium to a cyclic carbonate elegantly forms the desired ester. It's a recurring tactic in taxol syntheses using a precursor that neatly transforms into the target feature.
Using protection not just to block, but to set up a later transformation. Very clever. What about other approaches?
LiAlH₄ synthesis scheme 13.54 relied heavily on Diels-Alder reactions early on, even using phenylboronic acid as a template to facilitate an intramolecular version. He closed the tricky 8-membered B ring using a titanium-mediated reductive coupling of a dialdehyde, a powerful method for forming medium-sized rings, which are often difficult.
That B-ring closure seems like a common challenge. Any other ways it was tackled?
Another synthesis reported by a Japanese group, scheme 13.58, closed that B-ring early via a Lewis acid-induced Mukayama-aldol reaction. They also had a neat sequence involving a palladium-catalyzed cross-coupling to install a trimethylamethyl group, where a chlorine atom on that group later served as a leaving group for the final oxetane ring formation, that crucial 4-membered ring in taxol. It shows how you can plan functionalities, steps, even seemingly minor ones, far in advance.
Incredible foresight needed. Okay, let's look at ipothalone A syntheses, another complex natural product, another anti-cancer agent. What's notable here? Modern methods.
Yes. Ipothalone A is a macrolide, a large ring containing an ester. Its syntheses really showcase modern techniques. LiAlH's first synthesis, scheme 13.59, used macrolactinization, forming that large ester ring as the key closing step, a common but often challenging strategy.
And his second one used that revolutionary reaction.
Right. Olefin metathesis, scheme 13.60, used a ruthenium catalyst, like a Grubbs catalyst, to close the 16-membered ring by forming the double bond via metathesis. Super powerful reaction. The catch here was that it gave a mixture of Z and E isomers at the new double bond, which then needed separation.
So power, but sometimes with the selectivity costs, other ways to close that big ring.
Danishevsky, scheme 13.62, used a macro-aldol cyclization, forming the C2-C3 bond and setting stereochemistry simultaneously as the ring closed. He joined the fragments beforehand using the Suzuki reaction, another Nobel Prize-winning palladium-catalyzed cross-coupling reaction that's become a workhorse for connecting complex pieces.
Was there a way to get around the ZE issue from metathesis?
Yes. Förster's synthesis, scheme 13.63, is really neat. He used alkyne metathesis with a molybdenum catalyst to close the ring. Since alkynes are linear, you don't have ZE isomerism, you get the triple bond, which can then be selectively reduced later if needed. It avoids the separation issue completely. Very clever application of a related reaction.
Brilliant. Any other unique strategies for ipothalone?
Carrera, scheme 13.64, used a stereoselective nitrile oxide cycle addition, controlled by magnesium chelation, to set key stereocenters. His route also featured some less common reactions like a samarium diiodide SMI2 reduction. PENX, scheme 13.65, used chiral allylic silanes derived from enzymatic kinetic resolution, along with chelation-controlled aldol reactions and another kinetic resolution later on. A real showcase of multiple stereo-control techniques.
So looking back at the ipothalone work, what are the big takeaways, recurring themes?
A few things stand out. Lots of use of enantiopure starting materials. Common disconnection points were the ester bond for macrolactinization and the C12C13 double bond for metathesis. Modern catalytic methods like metathesis and Suzuki coupling were heavily featured for fragment assembly. The Wittig reaction was often used for building the side chain, and stereo control relied heavily on aldol selectivity or asymmetric methods like kinetic resolution. It shows a convergence on powerful modern tools.
Okay, our last big example, discodermalide, another macrolide, another potent anti-cancer agent, looks incredibly complex with all those methyl groups and alcohols.
It's a monster, stereochemically speaking, a real challenge. Schreiber's approach, scheme 13.67 and 13.68, was very logical. He broke it down retrosynthetically into 3 main stereotriad fragments, each containing a run of 3 stereocenters. He synthesized these fragments with high stereo control, using things like chiral boron reagents, and then coupled them using advanced methods like a nickel-chromium-mediated reaction.
Breaking it into manageable, highly controlled chunks again. Sensible strategy. What else stands out?
Marshall's synthesis, scheme 13.69, featured an early sharpless asymmetric epoxidation and used the LiAlH catalyst to create a Z-alkene specifically. Smith's synthesis, scheme 13.70, again relied heavily on oxazolidinone-cadein chiral auxiliaries for setting multiple stereocenters, followed by Suzuki coupling to join the main pieces. His overall yield was 9% over 17 steps, longest linear sequence, highlighting the sheer difficulty.
9% sounds rough, but for that complexity, maybe it's actually pretty good. Shows how much effort these take.
It really does. Pennock and Erfolov's synthesis, scheme 13.72, was even longer. 42 total steps, 27 longest linear, but achieved 21% overall yield. It relied heavily on boron enolate chemistry and allyl silane synthons. And then there's the Novartis scale-up synthesis, scheme 13.73. This is super interesting because it's about making it practical.
Right, taking it from the lab bench to potential production. What changes did they have to make?
They had to swap out reagents for ones that were safer, cheaper, or just work better on a massive scale. For example, using LiBH₄ instead of LiAlH₄ for reduction, or TempoBleach instead of Swern oxidation. Things that are fine in a flask can be problematic in a giant reactor.
Did the reactions work as well on the large scale?
Not always. They found one key aldol reaction dropped from over 75% yield on a small scale to only about 50% yield on a 20-25 kilogram scale. Scale-up introduces new challenges, mixing, heat transfer, concentration effects, a whole different field, process chemistry. They even had to develop a way to recycle the undesired diastereomer from one step back into the desired one to boost the overall efficiency. That's crucial when making extensive drug candidates.
Wow. A glimpse into the practical realities beyond the elegant lab synthesis. Okay, let's pivot now. Beyond these individual masterpieces, the chapter discusses broader innovations in how synthesis is done. Let's talk solid phase synthesis.
Right, this was a major paradigm shift. Instead of doing reactions in solution with everything dissolved, the core idea of solid phase synthesis is that your starting material, or the molecule you're building, is chemically attached to an insoluble solid support, usually small polymer beads.
Anchoring the molecule. What's the big advantage?
Purification becomes incredibly simple. After each reaction step, you just wash the beads. All the excess reagents, byproducts, solvents, they just get washed away, while your desired molecule stays attached to the solid support. This eliminates tedious workup and purification after every single step, which saves enormous amounts of time and effort.
And allows for automation.
Exactly. Because the chemistry happens on these easily handled beads, the whole process, adding reagents, washing, doing the next reaction, can be automated in machines.
Sounds perfect for making long, repetitive molecules like peptides or DNA.
Precisely. Its most developed application is polypeptide synthesis, SPPS. Building proteins and peptides involves adding one amino acid after another, but the key here is that every single step, both removing the temporary protecting group, deprotection, and coupling the next amino acid, has to be incredibly efficient. We're talking yields well over 99%.
Why so high?
Because errors accumulate. If you're making a 100 amino acid peptide and each step is only 99% efficient, you end up with a very low yield of the correct full-length peptide contaminated with lots of shorter fragments. It just doesn't work unless the individual steps are nearly perfect.
How do they achieve that? What are the main methods?
There are two main protocols. The older TPOC protocol uses the tert-butyloxycarbonyl protecting group on the amino acid nitrogen, which is removed with mild acid like TFA. The FAMOC protocol is more common now. It uses the 9-fluorenyl methyloxycarbonyl protecting group, which is removed under mild basic conditions, usually with piperidine. This is generally gentler on the growing peptide chain. Both methods require protecting groups on reactive amino acid side chains as well, which are only removed at the very end when the peptide is cleaved from the resin support. You also need very efficient coupling reagents like carbonamides, DCCI, DIPCDI, often with additives, HOBT, HOAT, or specialized reagents like HA2 to ensure those amide bonds form quickly and completely. Sometimes capping steps using acetic anhydride are added to block any unreacted chains from continuing.
And this works for DNA and RNA too.
Yes. Oligonucleotide synthesis is also highly refined and automated using solid phase techniques on silica or glass supports. It's crucial for making the DNA primers used in PCR, gene sequencing, and other biotech applications. It involves sequential formation of phosphodester or phosphorothioate linkages, again using specific protecting groups like DMT on the 5-hydroxyl, and a cycle of deprotection, coupling, capping, and oxidation steps.
The automation and ease of purification must open doors to making not just one molecule, but lots of different ones simultaneously.
Exactly. That leads directly to combinatorial synthesis, The goal here is not to make one specific target, but to rapidly generate a large library of related molecules, often thousands or even millions of them, by systematically varying the building blocks or reagents used in a synthetic sequence.
What makes so many?
Primarily for drug discovery. You create huge structural diversity and then screen the entire library for biological activity against a particular disease target. It's a numbers game, hoping that somewhere in that vast library you'll find a hit, a molecule with a desired effect.
How is it done? Just running lots of reactions in parallel?
That's the simplest form. Parallel conventional reactions. You might have an array of wells, like a 96-well plate, and run different combinations of starting materials and reagents in each well. It works, but you still face the challenge of purifying and characterizing potentially hundreds or thousands of individual products.
So solid phase helps here too.
Immensely. The really clever approach combines solid phase synthesis with sample splitting, often called split and pool or mix and split.
How does that work?
You start with your solid support beads. You might divide them into, say, 3 portions and react each portion with a different first building block, A, B, C. Then you pool all the beads back together and mix them thoroughly. Then you split them again into maybe 4 portions and react each portion with a different second building block, D, E, F, G. You keep repeating this. React, pool, split, react.
So each bead ends up with a unique combination of building blocks.
Exactly. Each bead essentially records a unique synthetic history. But the big question is, if you find one bead that's biologically active, how do you know the structure of the molecule attached to it, since they were all mixed together?
Right. How do you decode the bead?
Several ways. Sometimes you could do the biological assay directly on the bead, but more often you use tagging. The most common is chemical tagging. Alongside adding your building block in each step, you also attach a small, unique chemical tag molecule to the bead that identifies which building block was added in that step.
A molecular barcode.
Pretty much. At the end, if a bead is active, you cleave off and analyze the sequence of tags, often by mass spectrometry or gas chromatography, to read the barcode and deduce the structure of the active compound. The source mentions a library of over 3,000 spiroxyndals made this way.
That is incredibly clever. Is there anything even more high-tech?
Yes. The source mentions microreactors with radiofrequency tagging. This was used for making libraries of epiphenol analogs. The solid phase resin is contained within a small porous capsule, like a tea bag, but this capsule also contains a tiny radiofrequency, RF transponder chip. Reagents diffuse in and react, but the resin stays inside. At each split step, the RF tag on the capsule is electronically scanned and recorded, along with which reagent is being added.
So you track the history electronically, not chemically.
Exactly. At the end, you find the active capsules, read the stored electronic history from the RF tag, and you know precisely which sequence of reagents built the molecule inside. No chemical tags to analyze or potentially interfere. It's a very sophisticated way to manage huge combinatorial libraries.
What an amazing progression from painstakingly building one molecule to creating and tracking thousands or millions almost automatically. We've covered so much ground in this deep dive.
We really have. We journeyed from the core ideas of retrosynthesis and those essential tools like protective groups and synthetic equivalents.
Right, through the importance of convergent synthesis for efficiency and the absolute necessity of controlling stereochemistry.
To seeing these principles come alive in those incredible syntheses of complex natural products. Juvabione, longophyllene, prelog lactone, bicatin III, epiphenol A, discodermalide, each one a story of challenges and ingenious solutions.
Yeah, seeing how chemists plan, adapt, innovate, using this huge toolkit of reactions, rearrangements, cycloadditions, catalytic methods, enzymes, it's just fascinating.
And then finishing with the shift toward solid phase and combinatorial synthesis, enabling the creation and screening of molecule libraries on a massive scale.
This deep dive really drives home the incredible creativity and the relentless problem-solving that defines organic synthesis. It's so much more than just mixing chemicals, isn't it? It's truly designing and building at the molecular level, art and science combined.
It really is. And this ability to construct molecules with such precision, atom by atom, is what gives us new medicines, advanced materials, and fundamentally a deeper understanding of life and the world around us.
And you get the sense they're always pushing, right? As we saw, chemists are constantly looking for better yields, more efficiency, more elegant routes, more precise control, always striving for the next breakthrough.
Absolutely. So what's next? What are the big future challenges? Maybe tackling even more complex natural products, or designing molecules with entirely new, perhaps unnatural, functions, all while trying to make synthesis greener, more sustainable, more atom economical. The quest for molecular masterpieces definitely continues.
It's an exciting frontier. Well, thank you for joining us on this deep dive into the world of multi-step synthesis.
We hope you found it informative and maybe even a little inspiring.
We hope you feel well-informed and walk away with a real appreciation for the molecular architects shaping our world. Until next time on The Deep Dive.